All right, welcome to lecture 6. Today we are going to discuss mostly about the risk assessment, and so that's mostly on how do you know what is risk, what constitutes the environmental risk, and what increases the risk. How do you minimize that risk or exposure? So all that factors will discuss today. The reason this is discussed before even you go to the exposure, all that is because once you understand the risk, you know how to minimize it. The one way to minimize any risk is minimizing the exposure, and that exposure depends on the air, water, because you can expose to these contaminants by different route. So rest of the lectures that you will see in this class is more about how contaminants move in those systems, about the pathways. So today we'll just discuss briefly about what is risk and how we can calculate those. So before that, I just want to mention again, we had some conversation before the recording is that homework due tomorrow. Okay, tomorrow Thursday, unless you ask for extension individually for any reasons. Um, so try to submit by tomorrow midnight. It should be uploaded via Gradescope on CCLE. Homework 3 is due, which is going to release today. The homework 3 is pretty straightforward. It doesn't have much quantitative questions. It will be mostly your, there will be some essays. There will be first question will be essay about your interest on any specific topic on environmental engineering. So that's like a free choice, whatever you want to discuss. The reason is I wanted to get an idea of what really you feel important or what you wanted to learn or what things that bother you about environment, because based on that, at least I'll get a sense of how students want what students wanted to know. So the next lectures are very specific topic related to groundwater, surface water, wastewater, air, hazardous waste. There are many different types of topic. So those are application of what we learned today or learned so far. So based on your interest, I'll be trying to incorporate those materials as a into that context of that particular classes. So write freely because it's graded for whatever you can write. It's really not there is no right answers. And then there will be some questions related to risk. Those are mostly short questions. The examples are given already in the textbook, so you will just read those examples and see if you have any difficulty. But we will, if you have difficulty understanding those, because we'll not cover that here, at least I will not solve it right here. These are straightforward, but still, if you have questions, just ask on Campusware. I really prefer Campusware compared to individual emails. Even if you are sending individual email, you can actually email or contacted. You can contact me via Campusware without sending to the through whole class. Compared to emails, that is very organized because I can go any other times. Whereas on email, it can be buried. So if you send me email and I have not responded, maybe I have not read it because it's buried through other emails. So don't hesitate to email me again if you don't get response within 24 hours. Okay. So quiz will be released at midnight today. The reason I midnight is some students ask for more time because they have class entire time tomorrow until 5 p.m. So that means they will not have time to actually work on quiz during the office during the regular work hour. So I thought let's make it on entire Thursday. So we'll release midnight, so you have 24 hours. So hopefully that will give you enough time to work on at least 20 minutes some point in next 24 hours. Um, there is a question on annotated slide. I probably forgot. So let me upload the annotated slides today on class for Monday as well as today. There will be, so the quiz is 20 minutes. So it will block you out after 20 minutes unless you have a reason for all the extra time provided by CAE, Center for Accessible Educations. So everybody who asked for that through that CAE, I have not read the request, but everything is granted. I've never really say no to any of the requests like that. Again, my goal is for you to have enough time to work on the quiz. And as I said, during the regular class hour, students has usually the student have less than 12 minutes or around maximum 15 minutes. 12 minutes is the actual time, and usually by the time I get it from them, I give plus minus 2 minutes. I don't really try to take this out. So
Professor.
yes.
So you said that the quiz is going to be released tonight and it's going to be all day tomorrow open, right?
Yeah.
Okay. Because another classmate of mine who's going to hop into the lecture soon, he's in another lecture. He said that he needs to do it today. I don't know.
So that you can, if you have concern about this, let's say you're flying, you're flying, taking air, you know, flying to a different continents, all that stuff, send me email individually because I can arrange for that specific kind of request. But I assume that you'll have, everybody should have 20 minutes in the entire day. But again, I'm assuming. So if you have very special circumstances, I always encourage you to contact me. Um, okay.
Okay, thank you. I'll let him know.
Okay. Um, all right. So that's all for the announcement, and we're going to discuss about risk assessment today. And the textbook chapter 4, I believe it, chapter 4, but it's released or it's uploaded on CCLE, the PDF. The page number 127 to 162 is almost like the entire chapter. What I want is that you guys read those to understand it. But if you understand everything on the slides, then you don't need to read now. So I think just looking at the slide, if you understand everything well, that's great. If you don't understand, go back to the textbook. Then also you have to do the example problems, and during the example problems, you'll realize that you don't understand everything on the slide. Then you have to read those. So I don't, sometimes it's helpful for you to just look at the slides and try to understand, and then try to solve the example problems. And then if you have question, go back to reading those specific sections. Because, you really I don't want you guys to read everything, unless it's required. Um, all right, so today's learning objective is mostly on risk assessment. Means, how do you determine how much risk certain kind of pollutants poses to you or environment. So there are the learning objectives. I'll give you some real world applications so that you learn how to apply this concept. Then we'll discuss about different types of risk, basic risk types, and how to calculate this. And the end, we'll also think of, identify different hazardous substances which cause risk to you. So those are very, very basic steps. But what's most important is the how to calculate risk or how to measure risk. Because when you think of, how much amount of dose is a risk to you. For instance, a lot of time people say risk means chemical. Actually, everything can cause a risk. Okay. Um, so that means, let's see what I say. There is a question, is it under week 3 you uploaded homework too about mass balance again? I didn't understand the question. It says I uploaded
Maybe
homework too, or
I think they mean that like for homework through for week 3, shouldn't it be homework 3 that's getting uploaded and not last week's homework?
it's not last week homework. So homework 3 is going to be uploaded today, and it's due next week. Is it something homework 2 under week?
Professor, under week 3,
Yeah.
you uploaded homework 2 again.
Oh, I have to check that one. Maybe I made a mistake. What I did is I uploaded homework 1 solutions, I thought, but maybe that's a mistake. I'll check that.
Okay, thank you.
I mean to upload homework 1 solutions, which might be helpful for you for the quiz. All right. So again, these are the objectives, just in case you want to come back. All right. So risk assessment. Now, risk assessment again is about how do you know what amount is risk? For instance, think of, if I say, no, is water a risk to you? Well, everything can be a risk. When I think of risk, I'm talking about eating those or engulfing it. I'm not talking about accidental risk, all that stuff. Talking about you eat something and whether that causes a risk or not. Um, so you should think of water. We drink water, but if I give you the very pure water, something like water doesn't have any minerals. Think of DI water or milky water, which is extra pure water. And if I give you 2 liters of water, and I say that is this a risk for you? How many of you think it's a risk? Let me do a poll here. That's an interesting question. A lot of times students get it wrong. So I'm just going to put a poll here. Um, let's type it. I'm just going to say the per day you're supposed to drink 5 glasses of water, or 5 or 6 glasses. Let's say 2 liters. 2 liter of, if you drink 2 liter of ultra pure water, would it be risky? So that's my question. Answer yes. You can say yes. You can say no. There are 2 options. Okay. Okay. So yeah, I'm gonna pull on this poll. Oh, there is a spelling mistake. Just ignore that. Um, so if you drink 2 liters of ultra pure water, would it be a risk? Um, all right, 85% voted. Let's see if once we get more than 90%, I'll close it. Um, right, few more students, make it 100% now. Okay, so now it's slowed down. So I'm assuming the rest of the students are not in front of their computer. So in the poll, I'm going to share the results. So as you see, 90% or 70% students think that this is risky, and 30% says not risky. Right, I'm not saying that how much a risk. I'm saying just whether it's a risky or not. Is it something that you should engage or not? Again, here the question was ultra pure water. I'm not talking about the regular water, pure water. Something doesn't just H2O, doesn't have any minerals, any salt. Natural water, it has minerals, salt, because it goes through the rocks and it dissolves those um, minerals. So now I need some volunteer who would say why it is risky, you think?
I
And
think oh,
yeah, go ahead. Well,
I said I think it's risky because not of like the type of water, but more of like if you drink too much water, you can get like poison from that just because you're drinking way too much. But I'm not
so
sure if that falls near that.
let's put it this way: two liter is not too much. 2 liter is something that daily you have to intake that much water. So it's not the quantity. So think a little bit more.
I think
Yes,
because
too much water is bad, but 2 liter is not too much. So let's think of something else.
Is it because your
there's
water
no
doesn't
like
have like minerals you need for your
solute
body?
like dissolved into the water, like the solutes that are in your cells would like leave the cells, which would like cause your cells to like die basically.
Yeah, Kelly, you are right. So if you think of, I said ultra pure water. Ultra pure water means it doesn't have anything. Okay, so when you think of water, water is very toxic. Okay, if you put water on a very pure water in on rock, if you put a rock inside a very pure water, it dissolves the minerals, right? That's what it does. uh, so if you do the same thing inside our body, it also dissolves minerals. Think of our bone or cells. They have nutrients, they have minerals. For instance, our bones are made up of calcium phosphate. So if you drink that pure water, the calcium will dissolve. Okay, the minerals will dissolve. The kidney will have lots of these minerals that will dissolve. So if you drink ultra pure water, your body is going to start dissolving. Not like the mass or the fat will dissolve, but most of the minerals will dissolve. It will imbalance the sodiums, potassium imbalance. The cell does those kind of mineral balance to survive or to do certain function. That function will diminish. And when that happens, and obviously it causes massive issues in our internal organ. So that's why ultra pure water is toxic. Okay, and drinking too much water will have also similar effect. Now, even though it has some minerals, but if you drink too much, things will dissolve slowly. But so it's really not helpful to drink way too much water. So what it means that this exercise will learn that uh, everything that you think is not toxic can be toxic. Okay, and that's because because of the issues related to the quantity as well as the quality. Okay, a lot of times we think of quality, uh, uh, but not in terms of the the quantity. Okay, all right. So let's see on that. Let's get to the other sections. Let's see. I think it's wrong here. Right, so there are some real world examples. So for instance, in this particular YouTube video, if you click it later, there is a lawsuits because of contaminated land near a school or near a properties. So that how do you know when you buy a home whether your land is polluted or not? So that's why you have to, a lot of times you have to do these assessment studies. If you are if you wanted to also do some kind of property sales, or you have to also give that certificate that this is not polluted. So that's based on a law and a liability law circular. So for that you have to have some understanding of risk. So if you have engineers with a risk assessment as your measure, you would be doing that kind of job. And then another thing is pretty recent news, and it says that why dangerous forever chemicals. They call forever chemicals is because that's for fluorocarbons or carbon fluorine, any chemicals that contain this carbon fluorine bond. Again, it come back. Carbon fluorine bond is very strong. They had to dissociate, so that's very persistent. And it turned out it also caused cancer to at very low dose concentrations. So this is just the news. They found out that their water is polluted with a toxic chemical PFAS, and that could cause a health effect in children's, so learning delays, sometimes birth defect, and can cause cancer. Oh, wow, this noise is going to be bad. University is building this house, so we have to accept that. Um, All right, so this is just another thing. You have to know what concentration is toxic. And then there is this third one. This is another example is that, every year, tens of millions of new chemicals are introduced into the market. And we can't really test all of them. Okay, that's just not possible. So that's why science is lacking behind. Now we can't really test stuffs like I'm glad that you are not hearing the construction noise, but I hear it. Maybe this microphone is good. Um, so that's it's easy to say that this chemical is bad, but at the first place, why even we use that chemicals? A lot of times it's after like 10-20 years we find out that this is bad. So wouldn't not be interesting if or not interesting, helpful for all the chemical company to go through this assessment before even they introduce something in the market. A lot of times chemical company, they find this is very good. For instance, PFAS, there are some evidence that they knew this is going to be a bad problem, but they do that kind of assessment, but they cover it up because that's going to earn the billions and billions of dollars. Think of all the Teflon materials that you use. It's made up of PFAS. Teflon is PFAS. So all the utility, every person who use any kind of even in your dress where you want something water resistant so that it doesn't get wet. Even if you go to a restaurant and you see there is a tablecloth, and if you put a drop of water, it kind of doesn't wet it, like stay as a bubble. And that's because it has those water repellent chemicals, and that's actually PFAS. So it is used for many different products, thousands and thousands of products. Now just we realize that now, not now, in last 10 years, we realize it can be toxic. So this is the issues. This issue is not going to go away. We have to determine what causes toxicity. So you have to have some people who are interested in understanding what kind of chemical structure that cause toxicity, and some group of engineers who will be associated with measuring the toxicity effect, so more toxicologist or biologist. And then some engineers, like majority of environmental engineers, they look at after the fact. Well, now we know that it is toxicity, what kind of exposure will have, how much exposure will have, where it is going to migrate. All that we'll discuss in this class, not today, but throughout the lectures. So the first thing to know is how toxic a substance is, the method that we try. When you think of toxicity, there are two forms of toxicity, acute toxicity and chronic toxicity. Acute means think of that cause like poison, which cause immediate effect. For instance, if you give potassium cyanide, that's acute toxicity. You see these James Bond movies or all the movies, they take a tablet and they die. Okay, that's acute toxicity, means immediate effect, things happen immediately. Okay, whereas um, I'm just going to write it so that Bond movies, cyanide was extremely toxic. That's acute toxicity. When you think of chronic toxicity, that's something that we take a small amount, which doesn't cause effect immediately, but over time you get exposure to those and it cause disease or adverse effect. For instance, PFAS. Um, if Kevin, you were talking something. All right. So if you have PFAS, you are drinking PFAS. Those people in Philadelphia, they are drinking PFAS, but they didn't really have any effect immediately. But over time, it will cause cancer or it may have some defect. So those are chronic toxicity. So that those are something most relevant for us, because anything acute toxicity, we can eliminate them by just not using those products. But chronic toxicity is hard to know because we'll use those most of the time. For instance, lead. You have lead pipe, you have lead used in many products, but we just have to minimize that exposure. So now that you know what cause types of toxicity, now how do you assess tox risk? Think of this risk assessment, this diagram, which is kind of first thing is to do is identify risk. Identify the hazard. So that's all about chemicals. You have a chemical like cyanide or PFAS. You have to know whether they are toxic or not. Once you know they are toxic, they have to manage a different way. But it bring to the same question: how do you know this is a risk? Because risk can be eliminated two different ways: by not taking in a doses that is toxic to you. For instance, if you think of exposure assessment, you can use lead as long as those leads are not in your water. It should be fine. So that's why a lot of time when you think of lead pipe, there are ways to minimize that risk by not using water that is highly corrosive. So as long as your pipes are protected, it should not be a problem. Just because you use for instance, silver is toxic if you have dissolved silver. Doesn't mean that you cannot use silver as a bracelet, because that's not toxic to you. So it's a mode of exposure is also a factor. And so that's why the first thing is to minimize that exposure around. So that's the environmental aspect of it. Okay. The second is, if you cannot minimize exposure, you have to lower the concentrations, because that's all about dose and response. How much dose is going to become toxic to you? As long as that concentration is lower than that dose, this should be fine. For instance, lead. Lead has a limit how much lead you should have in water. And so as long as those concentration is lower than that amount, and it's calculated for your entire lifetime, and that amount of dose is not going to be difficult or not bad for you, then it's okay to drink that water. So that's why, because of this, all the drinking water has a limit. Okay, if you think of lead is toxic, but you don't have to have high amount of lead. For instance, I don't remember, I think it's 8 ppb or something. I have to check. So part per billion. So if your lead concentration in water is less than 8 ppb, it should be okay. So that's how, these are all determined by the dose response curve. How much amount of dose is toxic over lifetime. Okay. Once you know the dose, you minimize in a system. You know the concentration. You know the exposure route. Then you merge them together and see how much amount you are exposed to, and that is risk characterization. Okay, once you determine that, you have to manage it. Risk management is about policy, is about, how do you minimize all that. It's not about engineering. Okay, so again, dose response is all about concentration. What concentration is toxic. Exposure assessment is which route you are going to get it. If you get lead by air, is very different toxic than if you get lead by water. So this is more about, is it water, is it air, or is it food? Which form you are getting, because it may have very different amount of toxicity based on where it is exposed. For instance, asbestos. Asbestos is carcinogen, but if you drink asbestos, it may not cause that much harm. But if you inhale asbestos, that causes lung cancer. So through air, it is more toxic. So that's why it's important to know which mode you are going to receive. Okay. So this is just a exposure pathway. I just show you. This is your pollutant. You can expose the exposure pathway could be air, because of wind, or it could be because of water. It goes to groundwater, and then it goes to groundwater. Then you have a drinking water well. You take that water and you drink. That's how another one. And then maybe you can directly interact with the soil. Okay. Children's, for instance, lead exposure, it may not be water, but it may be because they're eating those sand. A lot of times the dirt has lead in urban area, and the children's, they play with the dirt, and they sometimes they eat those dirt. So that could be a part of exposure route. Or it could be food. If the soil has pollutant, the the pollutant will go to the tree leaves and all that, and then you eat those leaves, or the animal eat those leaves. They could be toxic. For instance, mercury. If you have a lake, um, the water can be polluted with mercury because of all the depositions, and the mercury partition into fish, and then you eat those fish, and that's how you get mercury count into your body. So you got to know all the possible exposure pathways, and we'll cover rest of the class is all about this exposure pathway. We'll see how pollutant move in water, air, all that factors. And in those classes, these are the things you have to understand. When you think of soil, we have to think of what kind of mechanism that makes contaminants stick with soil, how they release those factors. So there are certain parameters like Henry constant for air, vapor pressure for air, all those thermodynamical constant. These are uh, thermodynamical constants for a pollutant. So the idea here is that if you know these constants, you will be able to calculate how far they could migrate, or how far they could be present in that system. So these are again going to be in the part of the following classes, week 4 onward, just so that you have a picture of where we are going in this class. But today is all about risk. Okay. Again, just risk is determined experimentally. For instance, if I say how this is a risk, somebody has done this experiment. Usually they use some kind of animal models. They use animal models. So animal model to assess risk. They use rat, rabbit, monkey. As you know, it's rarely used by human. Okay, but they assess the concentration in human body, and they try to make infer those things. So most of the time, because I know it's not ethical, but this is the way people do. Okay, there is no alternative way right now. Over time, there are machine learning techniques. People are using those more. That reduce the amount of time we have to actually do the testing. But some point you have to test it. For instance, we are testing right now coronavirus antibodies or coronavirus vaccine. When you take that vaccine, it can cause also effect. So there are many human volunteers to see those effects. So there are sometimes human trial, but those are very end of the all these things. So again, the point here is that we determine toxic doses, how much doses is toxic to a certain animals, which has similar properties to us or mammal. And then once we determine the concentration for that cause effect in these animals, we extrapolate to human. Okay, and that extrapolation has certain mathematical functions. So we'll discuss that. Okay. So for instance, carcinogen. So these are the different types of chemical I show you here. Metals, which is arsenic, chromium, chromium 3. So chromium 3 is non-toxic or non-carcinogen. Chromium 6, hexachromium, is toxic. So as you can see, by changing the redox state, you have different types. So sometimes exposure management is all about changing the redox state, not removal. Just make all the chromium 6 as chromium 3 by reducing them. So your design will be mostly on that. Then you think of all the organic pollutants here, they can be toxic. The point here is just so that there are many chemicals that you already are aware of that could be toxic. But now how to determine whether it's carcinogen or not? So usually what they do is they take at least two species, either mice or rat. Um, so I'm saying, the female in that way. So they take 50 males and 50 female for one testing, and they add at least two doses, okay, with a no dose control. So that means you determine the concentrations that you want to evaluate, and you administer to 50 males and 50 females same amount of doses, and you keep doing the same thing as soon as you change the concentrations. So that means you see, they do that and they observe them, and they see for 6 weeks to 24 months. Um, Usually the amount of dose they give is very high concentrations, because if you give so small concentrations, you may not see that effect within 2 years. The reason is why 2 years? Because you don't want to do this experiment forever. So that's why they have to increase the concentration artificially high, even though that's not the hard exposure would be in real world. And once they do this one, they look for those effect. As you see, this is very extensive studies, takes a lot of manpower. Certainly, there are a lot of lives involved here. Lots of animals die because of that. And then it cost. That's why it costs something around half to 1.5 millions, 2 to 3 years of time to determine the toxicity of a single pollutant. And sometimes it takes even longer. So you can see thousands of animals die because of that one doses response curve. Um, and that's why it's very difficult to actually test for every single chemical. That's why we need some kind of machine learning techniques to understand based on what we know. But point is, take aside the ethical side of it. Now, we humans are selfish. We do damage the environment. We do a lot of stuff to survive, and so this is just one of those. Um, as you see, the concentration, the graph that you ask for, or a lot of times when you look at the chemical, they give you this kind of graph. What it called is dose response curve. It means you give, as I say, you increase the concentrations or doses. Usually the unit of dose is amount of mass of contaminants per unit mass of the body, okay? Because the toxicity is based on our weight. So that will be milligram of chemicals per kilogram of your body weight. This way we can normalize our chemical. either way, so you give different amount of dose to those mice, okay, and then you observe how many percentage of those mice has effect that you are monitoring. In this case, the effect is mortality, means how many of them die in that 2 years of the time you're given. So you'll get a curve like this. The very small doses, you'll see very small percentage will die. So as you increase this one, a lot of times the is increases. After a point, even you give more, it doesn't really matter because all of them die. Okay, so you'll see like a plateau. Okay, so this is called, so this is percentage death. This is 100%. This is 0%. And so the idea here is that, as you see, every single data points require lots of animal sacrifice. And then what you do is you see, the concentrations, you see at what point 50% of them die. So if you draw a line here, this is 50%, you are going to get a corresponding amount of dose that cause 50% to die. So we call that LD, or lethal dose 50. Okay. So if you know lethal dose 50, you will be able to say if this pollutant is more toxic or not. So now, if you see, for instance, this chemical, just because lethal dose is different, you see the curve can be very different. For instance, chemical A, this is the curve, and then you get LD50 is this amount. If chemical B, this LD50 is this amount. But sometimes the curve is not very similar. Like for instance, one is like this here, chemical C and A. If you see, LD50 is for chemical A is here, and for chemical C is here. So what does that mean? It means that it's interesting. Chemical A is not having a high toxicity at low concentrations. So at here, if you think of this is your contaminant concentrations, chemical C has more toxicity, more mortality at low concentrations, whereas chemical A has low toxicity, or chemical C has high toxicity at low concentrations. So you have to see those effects. A lot of times you have to think of what kind of chemicals you have and what concentration you are exposed to, and then you look at the lethal dose, all that.
I have a question.
Yes.
Why is C more toxic than A? I feel like shouldn't it, since it takes more of it to kill 50%, shouldn't it be less toxic?
No, so it depends on concentrations. Okay, so you're right. LD, based on LD50, chemical C is more toxic. But imagine if you have because this is a arbitrary different concentration, right? So imagine you have a water, lake water. This is lake water concentrations. So in nature, the concentration in nature, what you experience could be very different. That could be very lower than the LD50. So at that time, you have to evaluate whether this is more toxic or not. So LD50 just give you an idea of whether this is more toxic at certain doses, what amount doses require for them to kill 50% of the animals. But in environment, that concentration could be way below the LD50, and there you have to make the assessment. So in this case, the dose response curve will help you. For instance, here, if your environmental concentration is somewhere here, you draw a line here, you see the concentration for chemical C is much higher. Means at that concentrations, you have at least 10% will die. But when you think of chemical A, maybe nothing will die. Nobody will die. So you have to see the entire curve for that kind of cases. But if you are given LD50, you have to make assessment based on that. So having said that, there is a quiz. Um, you have a chemicals I gave you, LD50. Chemical A is higher than chemical B. Which chemical is more toxic? That's what the question is. So let me um, create a poll again. Um, let's see. Edit. I'm just not going to write anything. I'm just going to answer A and B. That way you just more right. You see that question um, on the slide, but answer through the based on what's there. So I gave you two chemical A and B. I just give you LD50. And based on that, can you say which one is more toxic?
Are we assuming they both have linear dose response curves?
Yeah, you don't need to worry about the curve, just based on LD50. So LD50 of chemical A is high, okay? Means
The concentration is high. What it means?
so think of this.
Chemical is high.
Basically this, I ask you this question here now. Oh no, I don't look at that one, but I'm going to create a curve here. So this is B, this is A, this is B, this is A. So LD, this is LD 50 for B, this is LD 50 for A. So which one is more toxic? All right,
Professor, I believe
yeah.
the letters are mixed from the last chart that you showed us.
Yeah. Just take this one. The last chart was opposite.
Oh, okay, because I already answered. Okay.
Is there any way to change the answer, or this doesn't allow you the poll? Because I didn't change the.
I already submitted it.
So once you submit, it
Fine,
doesn't
no.
allow you to change. Okay, that's fine. This is just for education purpose. All right, so I end the poll and I share the result. Okay. So here, if you see, it says LD50 of chemical A is higher than B. So that means you need this much amount of dose for this to cause tox death. So that means your dose amount for A is much higher. So what it means that chemical A, even exposed to, or chemical B exposed to very small amount of chemical, you'll still have toxicity, poor toxicity. So that means B is more toxic because it takes little bit amount to have that effect. Okay, so that's fundamentals. So what I talk about there is if you see the curve, as I said, for this chemical A, what it means that at this point, you don't, below that doses, you don't have to worry about it. Okay. But what about if the chemical is cancerous? So that's why when you think of toxicity assessment, cancer is such a serious disease. That's why people think of cancer in a different way. Here, it means that below these concentrations, you do not have any toxicity for chemical A. But for chemical B, you may have a toxicity even at the very small concentrations. So what if the chemical A is carcinogen? Would it does it mean that you'll take the doses below at certain concentrations? No, because nobody wants to take any chance. So that's why for carcinogen, you have to assume that even a very small amount will cause cancer. So that means you have to extrapolate in a way that could make it like something like here. So instead of like assuming this is like 0, if you extrapolate here, you will see like these concentrations, something at a very low, just zoom it out. Okay. You have to pass it through origin. So that's another thing you have to think of. So that's why when you think of carcinogen, they always extrapolate at the very to the origin. Whereas non-carcinogen, there is a threshold. Means below that, you don't have to worry about it. So for carcinogen, the threshold is 0. Means if you expose to anything, you assume there is a risk. Okay. So for that reason, as I said, when you apply for pollutant, you have to think of whether it's a carcinogen or not. Then now factor is, you apply this kind of the this kind of math to you get a number for, let's say, mice or rabbit. How do you extrapolate that to human? The first thing you have to think is that we are not same. We have different weight. So a lot of times when you extrapolate by weight. Okay, but that just itself doesn't cover it, because human have a different defense mechanism. So when you do that one, you have to think of a little bit different ways. So first of all, as I said, for carcinogen, you have to go way the small level. You can use a mathematical functions based on the data, but as you see, this is really not fitting. Okay, uh, this is actual data. This doesn't really fit well if you do the modeling here. So you have to find different types of models. Number one. Number two, you can have a binomial model, so or polynomial models, so that it can fit perfectly like this. Okay, so for that reasons, there are mathematical equations that you see in the textbook. You don't have to go through that, but just know that there are different models for that. And once you determine the models, whether it's a linear models or whatever the things, you have to go all the way to the lower level, and then you extrapolate that. You zoom it out. Okay, when you zoom it out, you get at the very end you get a linear curve. Okay, and that slope of that linear curve is the potency factor. Means how much increase in doses amount cause what amount of lifetime risk. That slope is important, because you use that potency factor and multiply with the amount of exposure throughout the lifetime, you get the amount of risk that you can get in cancer. So that's why I see incremental lifetime risk is chronic daily intake. Means how much amount of lead, for instance, you are taking daily by drinking the water from tap, and you multiply that your lifetime or whatever the time, and the, let's say, 60 or 70 years or 80 years, and then you multiply that potency factor, you get a risk. If you get a risk more than certain amount, then you say that this is not appropriate. Okay, so that's how you calculate the entire lifetime cancer risk. So it's a very simple thing. You mostly, this is a chronic daily intake is given to you. CDI is given. Potency factor is determined experimentally, or that's something you'll be known in this class. You'll know from a table, and then you'll be able to calculate. If you don't know from a table, you will know from this graph. That graph data will be given to you. Okay. So this is just example. Just give you some other chemicals that we just discussed: arsenic, benzene, DDT, all those particular chemicals. These are all carcinogen. Okay, and then they have a different categories. Category A means more risk, high risk. Category B is low risk. Category D is lower and lower. Okay, and and then you see the potency factor. That's the slope. That's a very small level that says how much milligram of these particular pollutants per kilogram of your body mass per daily that you have to take to have a risk. And if it is, again, this is there are two type of potency factor: if you are inhaling versus if you are eating it or drinking it. So that's why you can see the one is for air, one is for for water. A lot of times depends on chemicals. Air route is not more toxic. Okay, for instance, lung arsenic. If you inhale arsenic dust, if it doesn't cause that much effect as opposed to if you drink by water. So those are all because based on which organ is going to affect it. Okay, but if you think of something else, let's say there is let's find something. Um, Potency factor for vinyl chloride. You see, if you inhale them, which is basically if you take some kind of um, glue, the glue that you buy from Home Depot to stitch a lot of plastic, and those glue, if you see, it says carcinogen because it has vinyl chloride. So that when you those are used to glue a lot of PVC pipe, and when you work with them, you have to use some kind of mask or put those in a very ventilated environment. So as you see, this is more toxic because it go to atmosphere much quicker. So the potency factor is different. All right, so now this is just a simple math. When I say risk, a lot of times people call it relative risk, attributable risk, and odd ratio. Okay, these are all same. It's a different way. The way it is calculated is basically you do these experiments where you add mice or you test it with the mice, and what you do is you expose them, and you also have a control where you don't expose them. And a lot of times, even you don't expose them, some mice will also develop disease. This is by nature. So you have to account for those factors. That that some mice will die irrespective of whether you have that chemical exposure or not. So to account for those factors, you have to think of some mathematical way to account for things that actually has a positive risk versus negative control. So this is the matrix that you use. You have exposed, non-exposed, and you'll get the amount of exposure, number of mice that develop the disease, a number of mice that didn't develop the disease. So that's the number, for example, here. Mm. So then you have to calculate that. So if you see the calculation here, relative risk is the fraction of those exposed who have disease and fraction of those not exposed who have disease. So relative risk is, for instance, here would be fraction of those which exposed who have disease. So that's 15 here. Okay, and fraction of those not exposed who have disease, which is C. They have disease even they are not exposed. So this is called relative risk. Okay, and so relative risk is one means chemical may not have any impact. What it means that even whether you expose or not expose them, it has the same effect. So that means the relative risk, if you say relative risk is equal to 1, that means the probability of having cause a disease is nothing to do with chemical, because you have equal probability causing cancer or not. So this is relative risk. If you go to another one, attributable risk, the math is a little different. That's like difference between the odds of having the disease with expose and the odds of having the disease without exposure. So odd of having disease is think of um, the difference between the odd of having disease with exposure. So odd of having, so this is a difference. So that means um, the difference between odd of having disease with exposure. So that will be um, you have 15. 15 people got disease. The odds of having disease without exposure. So that will be 15 divided by 15 people get. I have to check this one. What exact the math? Odd of having the disease with exposure, the odds of having disease without exposure. So odd of having without exposure is 450. Didn't get the 24 got disease without exposure, and 15 got disease with exposure. So this let me check, because I think I forgot the math, exact math, how they write it up here. We have few minutes left. So what I'm going to do is after this class, I'll check that book, or also you check this one. I'm sorry that I didn't even occur to me that I didn't understand this one. There is a difference term here, delta, difference divided by delta. So that's why the relative risk is 0, because there is a minus sign here. So maybe it's 24 minus 15, but let's check that one in the book. Then there is a odd ratio. So basically it says, as I said, it's a AD by BC. It just give you immediately the region. So that means A here is A is here, this is B, this is C, this is D. So this will be 15 times 450 divided by 24 times 185. So again, these are all just different ways. It doesn't really mean much. It means that different people use different types of calculations. You just have to learn what that definition is. Okay. So this is going to be more like a quiz question. This is not like something you have to remember. Okay. As long as you know the formula, you should be able to answer it. The last thing I want to say is for cancer, uh, when you extrapolate that, or for non-response, non-carcinogen compound, if you extrapolate to human, if somebody just come up with a dose response curve like here, at some point you realize there is a threshold, right? Threshold means at point where you don't see an effect after a point. Then the point is, a lot of times people are not comfortable in believing this data. They always want to have a range. So that's why what they say is, even you have a concentration like that, I wanted to have a range of where I don't have to worry about. So that's why they say there are two other things, uh, LOEL. So lowest dose and administered that results in response is given a special name. So for instance, LOEL means at some point, this one, experimentally you see a response. So for instance, you have a data here, you see some response, then you extrapolate back to that zero. So that's why it's called LOEL. NOEL means a no response, no observable effect. So this is means at the lowest concentrations at which there is no effect. Okay, once you know that, that range will determine regulations. You wanted to say that, okay, I wanted to have these contaminants with no, never within that range, because you still don't know what's the error yet. So that's why a lot of times people do is a reference dose or RFT. So that's basically acceptable dose, because that's way below that no response. Okay, so arbitrarily they choose that lower just to be safe, and then they use that concentrations to actually determine the amount of hazard you are going to expose. So this is just again just extrapolating and be safe, be in the safe side. Okay, so that's all in terms of the risk calculations. This is just not part of the textbook, identification of chemical with elevated risk. I'm just going to go over through very quickly just to give an idea, because these are the things will come up in future, just to adding that chemical aspect. So again, you don't have to remember all these things. This is again going to come back in future because you don't know the thermodynamic constants. First one, how do you know? This is all about exposure. Okay, if a pollutant is highly soluble, that means you have more likely to be exposed by water. So what you have to look for is solubility. If a toxic pollutant is more soluble, you have to think of is risk. That's why PFAS is a risk, because some of the PFAS is extremely highly soluble. Okay, so if the solubility goes high, I'm talking about it well, the exposure risk goes high. Okay, but if the solubility goes down, you might not be exposed by water, but what it means that particular type of heavy metal will more likely to stick with your fat, because it doesn't like water. That means more likely like the organic or the fatty structure. So that's why lead, if you think of lead, it has extremely low solubility. So that means a lot of time you may not see lead concentration high enough in water, because they will precipitate out. They will go somewhere else, and then it will stick with the organic matter. So that's why if you see leads, most of the time people apply compost outside there. If your soil is polluted with lead, you just add organic so that it bind with those and stay in there and doesn't go anywhere else. So same thing, there are lots of, as I said, this example I gave you. So these are all just to show. And this is just one example why mercury and leads bind with fat more than other metals. It's all about how the binding constant, what they react with. So for instance, if you see here, um, they divide into hard and versus soft metals. If you think of lead, let's look for lead, which is Pb. So this is palladium. Let's see, where is lead? I could not find that in the, let's say mercury, just to make it easier. Mercury is what you find is a soft. So that means anything soft base will be reacted with that. So if you see soft, these are the soft. And these are usually fat. The R, when you think of R, these are all fat. Okay, that's organic. So that's why if you think of mercury, they stick with our fat, our body, more than in water. So you will not find mercury high concentration in water. So again, don't think too much about it because we are going to cover that later. But just know that just by varying the oxidation state and all that, it becomes toxic. For instance, chromium 6 plus is carcinogen, chromium 3 plus is not carcinogen. All right, so I think these are all, I don't have to cover those things. Just know that there are many chemicals around you use all the times, whether it's a solvent, they are all carcinogen. For instance, this is for the when you burn any biomass, you get this pH. That's why anytime you have a wildfire in California, you are exposed to polyaromatic hydrocarbons. And these are from petroleum or gasoline. When you're exposed to those, when every time you go to pump gas station and you put those, you are exposed to those.
So
All
I
right.
have a quick question.
Yeah.
Could you just restate again? So if an element has a higher oxidation state, it has higher solubility as well. Is that what you were saying?
No. It doesn't mean anything. So the solubility can be different things. What it means that if you have oxidation state, different oxidation state have different toxicity. Okay, and that is determined experimentally. So you can't really you can find out just by looking at them. Okay, but here
Great,
it
thank
just
you.
chromium 6 has more toxic. And here just to show that now, whatever the metals that you are thinking of, just look for what they are going to bind with. The soft metal, which is here, they bind with the soft base, which is our body. Okay, but if you think of or some fat. Uh, Again, you don't have to remember any of these, memorize, because I'll not ask these questions on quiz, just so that know the context for toxicity. And there are lots of examples in the book. What I suggest is you go through these examples, and because the answer is given in the textbook, you should try to solve it. And once you finish solving it, if you don't understand it, ask those questions on a campus web. Because homework 3 will have at least 1 or 2 questions from
Professor, I had a quick question.
Yeah.
I had a question. So on the chart that says the hard and soft ones,
Yeah.
I saw PB was like in its own little category underneath where it says hard, I think.
Oh, I see.
PB2 plus. But I thought you had said that it wasn't soluble and it would stick with like our bodies instead. I don't know, I was just confused.
So let's put it, there are 2 factors here. One is solubility. Solubility determine whether they are going to bind with our body mass or not. Because word solubility means if when you drink them, it will be easy to also dissolve them and extract out of the body. That's why you see sodium and calcium, they don't stay in our body, they leave out of the system. But lead has very low toxicity, low solubility. That's why anytime you ingest them, they are going to bind with a lot of organics, so that's the reason. It says it has a, because of low solubility, it has more toxicity once it enters the body. Okay.
Okay, thank you.
All right, so I think now the last thing I want to say is just solve these examples, which will help you answer the questions in homework. The last thing I want to say is that the question is to what lecture does the quiz cover? This is as provided in the previous class, up to lecture 4, everything until the last week. Okay, nothing from this week will be in the quiz. Okay, so mass balance chemistry will be part of the quiz. Most question in the quiz will be from chemistry. The reason is that's part of the homework one. I uploaded the homework one solution, so just check those on Campusware or any other place. So that's conclude this class today. So I'm going to stop recording this one.